Okay, very good morning to all of you. So today this is module 1 we will be covering, and in continuation with the lecture 1 and 2, this is lecture 3, and in the first lecture we have dealt with the von Neumann architecture, and in the second lecture we did the bus structure and what are the different types of buses that are present. And this is lecture 3. We can discuss some numerical problems and defining the various types of what is clock rate and how we are representing the hexadecimal numbers and all these things we will be covering. Now, as you know that clock signal in the digital electronic circuits also you have used this clock signal. In the clock signal is nothing but a square type of signal which is used for completing one cycle. Okay, so if you see, this is a clock signal. So this clock signal consists of 1 0 1 0, this form of changes. Okay, so you can see it here that all CPU and bus operations are synchronized with the clock. Okay, so when we used to buy some PC or laptop, what is the clock rate is what is the processor speed? Basically that is nothing but the clock rate or clock signal rate. Now, like we have used the 2 gigahertz or 4 gigahertz, so depending on that, this type of clock cycle will change. Okay, so machine cycle measures the time for a single operation. Okay, so if you write a code, so multiple operations are there, so machine cycle is nothing but the clock cycle that is used for measuring the time to perform a single operation. Like one cycle means if it is a T on and this is T off, T on plus T off is equal to one cycle, or you can say, so starting with starting or ending with ending, the total time is one cycle. Now in this regard we can point out another thing that when we discuss about the clock frequency, we call it as the frequency f, and in this case the clock frequency is given by 2 gigahertz. So if it is 2 gigahertz means you know that 2 gigahertz is nothing but 2 into 10 to the power 9 hertz. Okay, so kilo is 10 to the power 3. So when we talk about the 1 kilohertz, that is nothing but 10 to the power 3 hertz. This is important because in the numerical questions we can change the frequency and we can ask that what is the clock cycle in terms of seconds. When it is 1 capital M hertz, that is 1 megahertz, this is 10 to the power 6 hertz. Okay, and third is 1 gigahertz, 1 capital G hertz, so this is 10 to the power 9 hertz. So in this case the clock frequency they have mentioned here 2 gigahertz, so it is 2 into 10 to the power 9. So we know the cycle time or the clock cycle time is 1 by f, so this is nothing but 1 by half into 10 to the power 9. This is 1 by hertz is nothing but second, so this is 0.5 into 10 to the power minus 9 second, so this is 0.5. okay, nanosecond. So from this we can calculate the clock cycle. So from here frequency we can calculate what is the clock cycle by using this formula T equal to 1 by f. Okay, now it is not a single operation. Suppose you are doing some operation or some program, like it is like a floating point operation of multiplication, and this operation consists of multiple cycles, like 10 to 100 cycles depending on the processor. Okay, this is the way multiple operations takes place, and depending on that how much cycle is covered, that is calculated. Another important term is the FLOP. FLOP is floating point operations per second, a useful measure for supercomputers to how much it is computationally effective. That is the source intention of using this parameter. Okay, floating point operations per second. Now at one simple problem we can understand that for any kind of translation from, we know that there are three types of language: high level language, then we convert this one into the assembly language, and then we have the machine language. And machine language is nothing but in terms of ones and zeros. Okay, so when we discuss about the machine language part, okay, so these are all hexadecimal values, because it is not binary, because hexadecimal means 0 to 9 and then A to F. So if the instruction is like this, okay, so you need to translate this language into some assembly language. So machine language is given by this. So how will you represent this? This type of question may arise. How will you represent this number into the assembly language? So as we know that each of the, so there are two basically machine language code. This is the first one and the second one. So the first one is 0 into 41FE83B3. Okay, so what we know that each of this is basically a hex code. So hex code means when you are converting into binary, so each digit is represented by 4-bit binary. So what is the binary of binary of this 4 in terms of 4 bits? So this is 0100, this is a binary of 4. Then you have this 1, so 4-bit representation of 1 is 0001. Then you have this F is basically 15, right? So if it is 15, then 1111, this is F. Then E is 14, so this is 1110, like that. So up to 3 is you have 0011. So the whole thing is basically the representation of binary for the first machine language code. Okay, and what is the, so the whole instruction is given in this form. So what is the means what is the opcode of this instruction? We know that at least the last 7 bits, okay, the 7 least significant bits. So if we write in the same line, so 011 0011, these are basically, you can write this one in the same line also. So 011 and 011 and 0011 is the 7 bits. These represent the basically the opcode for each instruction. This is for the first machine language code, and for the second machine language code you convert this whole thing into the binary. F is 1141, so you have 4 ones here. D is like this, so the representation in terms of binary is this, and you are taking the last 7 bits to represent the opcode. So this is the way you can find the opcode of this. This is a ARM processor, 32-bit. This is happening for 32-bit ARM processor. Okay. Now conventional numerical problems we can touch in this lecture. Like it is given, you can read the question. A program contains 1000 instructions. It is there, how many instructions are there? 1000 instructions are there. out of that 25% of the instructions requires 4 clock cycle. Okay, so what is the 25% of this 1000? That is 250, right? So 250 instruction is taking 4, each of the 250 instructions is taking 4 clock cycle. 40% of 1000 instruction is taking, each of them is taking 4 clock cycle, and remaining is taking 3 clock cycle. Now they are asking find the total time required to execute the program running in 1 gigahertz machine. So what is the processor speed is 1 gigahertz. So f equal to 1 gigahertz. Okay, so in one second actually 10 to the power 9 number of instructions are running. So what is the total time required? So to execute a program running in a so in this program how many instructions are there? So in this particular program 1000 instructions are there. So you have to find out the total number of clock cycle. Okay, so if you see the next solution, so total number of instruction is 1000. Okay, 25% of is 250 instruction, that is requiring, each requiring 4 clock cycle. 40% of 1000 is 400 instruction, each of them requiring 5 clock cycle, and 35% of n is basically 350 instruction. It is taking each of them is taking 3 clock cycle. Correct. So if you add the whole thing, it is giving you total 1000 instructions. So what is the total amount of clock cycle? So 250 into 4, so this one, plus 400 into 5, this one, plus 350 into 3. So this is the total amount of clock cycle. Okay, so what is the time for each clock cycle? 1 gigahertz means, if it is 1 gigahertz, frequency is 1 gigahertz means this is the 10 to the power 9 hertz. So what is the clock cycle or machine cycle time? This is 1 by 10 to the power 9 hertz, and that is nothing but 1 nanosecond. So each cycle, one cycle is taking a time for execution, that is 1 nanosecond. So what is the total number of cycles? 250 is taking 4, so this is the total cycle into this. So this many amount of nanosecond is required, okay, to execute the total program, which consists of 1000 instruction. Okay. Now you take another question. So you take time and read the question. So that second question says a digital computer has a memory unit with 24 bits per word. Okay. As you know, in the classes we have discussed, when we discuss about memory unit, so a memory is considered as this, and when we discuss memory, these are the words. Okay, words are stored here, and these are the addresses that are located. Okay, so word length means how many bits are there, that is specified in the question. So if this is the memory unit, the length of the word is 24 bits. Okay. Now the instruction set consists of 150 different operations. 150 different operations. All instructions have an operational code, opcode. So what is the instruction format? They are telling that one portion is opcode. This is the opcode. One second. This is the opcode, that is given in the opcode. And what is the second part? Second part is the address part. Okay, this is the address part. Now how many bits are needed for the opcode. How many codes are there? There are 150 different operations. So if this is 150, so as if 150 different operations means by how many bits it can be represented. Suppose there are 4 operations, so each operation will be represented by how many bits? 2 bits. So 2 to the power 2 is basically 4. Okay, so if 150 is there, so basically 150 I can write it 150. Okay, 2 to the power how much is less than 150? So 2 to the power n is just more than 150. That we have to understand. So it's a 2, 2, 4, 8, 16, 32, 64. Okay, then 128 and then 128 above because 120 is less than 150. So this is a bit more. So 256 is, so 2 to the power how much is 256? That we have to calculate. Okay, so it is 2 to the power 8. If you calculate, it is going to be 256. So as you know that I have told you the opcode portion is there, opcode, another is the address. Okay, another is the address. Now opcode portion, how many opcodes are there? 150 opcodes are there. So how many bits are required to represent individual opcodes? 8 bits. So 2 to the power 8 is 256. If I take 2 to the power 7, it will be 128. So few opcodes will not be addressed in those cases. Okay, so this will be representing 8 bits. 8 bits are used to represent the opcode. So total how much bit is there? They have told you in the memory. So this is basically the memory stack. Okay, and the instruction is stored here, out of which two parts are there, opcode part and address part. So opcode is 8 bits. So how much is remaining? So 24 minus 8. So 16 bits are remaining. That is the address size. So if it is 16 bits, so what is the address portion? So address is 2 to the power 16 is the addresses, and each location is going to hold the allowable memory is 2 to the power 16. Okay, so this is for all. Thank you.